Hey everyone, so obviously I've been a little bit MIA lately. Once again, I've been kind of busy with work and other things, which by the way, actually, this is probably a good time to ask for suggestions. Please comment down below in the comment section. What are your tips for motivating yourself to do things after work and on the weekends? So what I've come to realize that as a full-time employee, you don't necessarily have energy or motivation after you work and you've been thinking about all these hard problems when you're working. And it's like harder to do things that you actually want to do, which is sort of counterintuitive, but that's just the reality of it. So give me suggestions of how you manage your time and do things that and make time for things that you want to do. So a little life update. On Saturday, I'll actually be at a conference called AlterConf Austin. And my talk is called Looking for Attention, a talk on self-advocacy and building platforms, which I am super excited about. If you're in the area, I hope you get the chance to stop by and definitely buy a ticket and support the conference. Also, if you're a sponsor, I think they're looking for sponsors, so please financially support them. I'll also make sure to link down below of where you can donate or perhaps contact them for sponsorship opportunities. And today what I'll be talking about is Borg. The reason why I'm talking about this is because I've been interested in Kubernetes lately, and Borg is just always mentioned in a lot of the things I've been reading. It's a preface to Kubernetes, and it's internally used within Google. What I do want to say prior to getting into, talking about this stuff is that this video is a walkthrough of the Borg paper itself. So definitely use that as the main resource. I'll link that down below. And then also, John Wilkes, one of the authors of the paper, does like a really comprehensive and great video about Borg itself. And he kind of gives you the bigger picture of how Borg fits in and why they need to create it, and does like, he's really animated and awesome, and it's like really comprehensive and understandable. So I'll also link that video down below. He does it a couple times at different conferences and like speaking opportunities, but I'll link one of them down below. And the other thing that I will do is there's this paper, or this article, that sort of compares Kubernetes, Omega, and Borg, which Omega and Borg are both, also, again, prequels to Kubernetes itself. So that paper was pretty awesome. You should definitely read that, and I'll link that down below. I reference it in the beginning of my video as well. Another point I should make, sorry, this is like a really long intro, is that I won't be going into too much detail about scheduling with Borg. I'm going to save that for when I talk about Omega, because it's better to compare all three of them at once. All three being Omega, Kubernetes, and Borg, and how their schedules work. So let's jump into it. All right, so let's get started talking about this paper. So the paper is called Large Scale Cluster Management at Google with Borg. The link is down below with the PDF of the paper, as well as other sources that I've been checking out throughout the week. The reason why I was interested in reading this paper is because I kept seeing Borg mentioned whenever I was looking at Kubernetes stuff, and I'm just generally interested about Kubernetes because it's gained a lot of velocity in terms of large open source projects. So yeah, I figured why not read the paper and see what it is all about. So Borg as a background is sort of a preface to the Kubernetes that we have today. It goes Borg, Omega, and then Kubernetes. I'll probably talk about Omega in a future video. But yeah, so Google runs, right, at an incredible scale. So for instance, like we today have Googling as an official verb in the Oxford English Dictionary, pretty big deal, right? We use our applications every day. So You can think of Gmail, Google Search, Google Calendar, and that it's not hard to imagine that that attracts a huge web traffic, right? So with all this web traffic, there is a huge problem, right? So Google needs to be able to handle the scale. So the problem is that there are different machines that all need to coordinate to run different kinds of applications, so Gmail, Google Search, all that stuff, with different workloads at different times. So let's say, for instance, at 12 o'clock every day, everyone is surfing the web, or like there's common times at the day in different parts of the world that there's internet traffic. Or, for instance, there's unexpected internet traffic spikes. So like something happens in the world, some current event thing, and everyone's trying to like Google search about it, or that sort of thing. So this is the problem that Google needs to handle. So what Google did was create something that would manage all of their physical machines, right? So a group of physical machines is called a cluster. So what Google needed to create was a cluster manager to solve this issue. So they needed to create something that would be able to handle the load efficiently on all of their servers. And so Google's internal cluster manager is called Borg, and that's what I'll be talking about today. All right, so actually before we talk about Borg, let's first talk about, or rather mention containers. I won't actually be going into the details of what containers are, so you should learn about that on your own time if you don't know already what they are, or check back on my channel when I eventually get to creating a video about containers. My to-do list for videos is never ending, but I promise I'll eventually get to it at some indeterminate future timeline. So the paper, or rather the article that I thought was really illuminating was comparing Borg Omega and Kubernetes, and it's called Borg Omega and Kubernetes, Lessons Learned from 3 Container Management Systems Over a Decade. And so what you really need to understand before I get into Borg is that containers are sort of at the core of the solution. They are, the building blocks of what Borg is. And so what containers allow are they allow the infrastructure to cater to applications rather than the other way around, and having applications cater to the infrastructure. And they do this by allowing applications to be machine and operating system agnostic. So what this means is that application developers don't really need to actually think about the operating system or the physical machine details that it's running on. And this is because that containers encapsulate the scope of an application. So this ultimately means that the infrastructure can now focus on managing applications rather than machines. They also enable reproducible app environments, or rather, I just say easily reproducible app environments. So if you think about, let's say, Docker, for instance, right? That's like a popular technology that we use now. Docker, in order to be able to define your container, you need to define a Docker file, right? So those two are kind of like, you can't have one without the other. And so in Docker files, it's really easy to be able to spin up the environment with all the dependencies that you want for the application that you want to install inside that environment. And I added kernel level resource isolation because it sounded like a really important security point that I don't actually know too much about, aside from like the really superficial understanding of resource isolation. So hopefully that's also something I'll look more into the future. But it's something I thought was important to add because the article made a point to also highlight that as super important. So yeah, just to remember, so containers are at the core of this. So what does this actually all mean? It means that aside from being a cluster manager in this
aside from Borg being cluster manager in the sense that Borg is, sort of manipulating physical machines, what it's actually doing is it is a container manager. It is manipulating containers on the machines. And that's just sort of the point that I wanted to highlight. And the other thing that happens is that because Borg can just concentrate on manipulating physical machines and containers or applications are installed within containers, and that like scope of your application is all contained within the container. That's a funny sentence. Is that Borg can also just focus on managing applications. And you can read all this in a much more eloquently stated fashion in that paper itself, which I'll also link down below. And that goes for me explaining Borg as well. All of this stuff is much more eloquently explained inside the paper. I'm just trying to take a stab at it as well. But yeah. Okay, so the first thing I wanted to talk to you about is sort of a general overview of what's going on, so that can kind of provide a basis as I go more in depth into Borg. So after this, I'll break down Borg in terms of the user perspective, and then also the actual Borg architecture. And then after that, some analysis that's in the paper. So that's actually how the Borg paper itself breaks down each of these different topics. So here's like sort of the overview. So what happens is that the user, which are usually Google's SREs, they can define a configuration file that defines a job. So I'll go more into detail about what a job is later, but a job basically defines some tasks and things like that that the SRE wants to run. And so what you can also define within this configuration file is, the number of copies, perhaps the number of copies as well as the program binary, so the actual program you want to run, and then which cell in the world that you want to run it on. So again, I'll talk more about cells later on, but for some brief context is that a cell is sort of a cluster of machines, somewhere in the world. It's a very large cluster of machines. And so for instance, if you specify an abbreviation, then that can define which cluster it runs some part in the world. Okay, so we have a config file which defines a job. Let's go ahead and circle that. Oops. Circle that here. Okay, so then we define the job, and then what Borg does is so then what happens is the user makes an RPC call to the Borg master. So what happens is that the configuration file gets stored into persistent storage. So the Borg master is actually replicated 5 times in sort of a Paxos-based store. I can talk about RPC and Paxos in later videos, but for now, just think of RPC as sort of a call to, like a function call to make something happen. And then the persistent store is just a way to persistently store information in a distributed way. Okay, so this configuration file is now stored into this persistent store within the Borg master. What happens then is the scheduler will, the Borg master will tell the scheduler to schedule this job onto one of these Borglets, onto one of these machines. And so the scheduler will say, okay, I pick, this machine here on the bottom left, and then it will tell Borg master which machine it picked. You'll note that the scheduler has scheduled this job. However, the job isn't actually yet running on that machine itself. Okay, so the scheduler just picks which is the correct candidate to schedule this job, and then Borg master now has its persistent store updated. And then what happens is the link shard will make sure that each of these, the machine states are what is against or what is defined in their respective job configuration files in the persistent store. right? So what is a Borglet? A Borglet is sort of this agent that's installed onto the machine that will make sure that it has the correct state and has the correct jobs, and the jobs are running in the correct state within that machine. Okay, so that is sort of what the link shard maintains. So it says, okay, is that job running on that Borglet? No, start it up. And then it'll also check to see if that job is in the correct state. If not, what it'll do is it'll make sure that it's in the correct state. So depending on which part of the state machine it's in, then it can kill the job or restart it or a number of things to make sure that that job is running in the correct state and that the correct Borglet is running against it. So to give you sort of a brief summary again, the job configuration file will be pushed into the Paxos persistent store in the Borg master, and then via RPC call, and then Borg master will tell the scheduler to schedule this job. The scheduler will tell the Borg master which machine or Borglet that it has scheduled it on. And then it'll update the persistent store. The link shard will then go ahead and make sure that each of these machines have the correct jobs running on them. If not, it'll make sure the job is running on them. And if the job is not in the correct state, the link shard will make sure that the job will work towards, this desired state. So that is sort of a brief overview about what we are looking at. Okay, so let's get into the section where we sort of talk about what Borg is from the user's perspective. So the first thing that we should talk about is what the workload sort of looks like. So there's two kinds of workloads that run in a Borg cell. So the first kind is a service. So you can kind of think of these as these like long-running services or group of jobs that should never go down, and these are things that should always be available, and the request should be pretty short. So you can think of, for instance, Gmail, Google Docs, web search, or like really important infrastructure things like Bigtable. So again, these are things that should always be available, should never go down, and should have really short requests. And the other kind of workload are batch jobs. So we can talk about them sort of in relation to services. Batch jobs are not as important per se. So let's say a service needs the resources that a batch job is taking up. You can sort of kick out the batch jobs and have them rescheduled for later if the services need the resources that the batch jobs is using. So batch jobs are sort of these less important jobs that they run for a shorter period of time, and they're less sensitive to performance fluctuations. So for instance, let's say for a service, for instance, Google search, right? Something crazy happens in the world and everyone is all of a sudden using Google search and there's a ton of traffic, and that's more than usual. Services are more sensitive to these sort of performance fluctuations where, again, batch jobs, if a service needs to use the resource, batch jobs can be kicked off, okay? And the next thing that we can talk about for workloads are that, so we have these sort of two main differentiations for workloads, are that workloads can mix across cells. So we can have a cell that has 60% of its resources allocated to services, and then maybe 40% allocated to batch jobs or things like that. And each of these cells run a different mix of applications. Some cells maybe, the other ratio around where they have more batch jobs that are scheduled or using up resources. And obviously workloads mix over, the workload mix varies over time. So batch jobs, once they're done, they can leave and come and go. And we've talked about before how services can see sort of this pattern where perhaps there's, more traffic in the middle of the day in one part of the world, or more traffic in a part of the day in another part of the world. Some traffic can be sort of preempted. However, if they're not, services need to be flexible enough to be able to take on that workload. And yeah, that's sort of the high-level overview of workloads. And these are the two kinds of workloads that you'll see within a cell. So let's go ahead and continue with the user perspective and talk about the cluster. So that's this outer line that you see in black. A cluster is a data center that hosts one or more cells. So the cluster is the physical data center itself with, you can see these like bunch of physical machines in there that I have in this beautiful artistic rendering in gray here. And a cluster, once again, hosts one or more cells. And cells are just, a group of machines that are connected by a data center network fabric. Usually within a cluster, there is one large cell and then smaller cells that handle things like testing or other more specialized jobs or other more specialized roles, because I don't want to confuse you with the term job. Because job is an actual thing, as we'll see now. So a job is scheduled to run within a cell and are made up of tasks. Jobs are made up of identical tasks. And tasks are synonymous with a container. So tasks are containers. And they're basically just comprised of, each container is just comprised of Linux processes. So you'll remember in the overview image, was that jobs were submitted via a config file to Borg through an RPC call. And then jobs are then scheduled, and then the link shard will communicate with the Borglet to make sure that they're running on the correct machines. So that's just kind of a reminder of how this job got here. You'll also see this blue dotted line here called an alloc set, and all the alloc set is responsible for is for reserving the resources that one or more jobs will need to use and run on, so that it makes sure that, the jobs submitted here have enough resources to run within that alloc set. And that is sort of, the organization of how a cluster looks like. Okay, so the next topic that we can talk about is priority quota and admission control. Again, this is a section within the paper. I'm just sort of doing a walkthrough of the paper. And the question that the paper poses is, what happens when more work shows up than it can be accommodated? So this means, let's contextualize it back into the cluster again, is that if there's more jobs that require more resources than the cell can accommodate, that the job is being submitted to the cell to be scheduled, and if there's not enough resources, then it shouldn't be scheduled, right? And this is where we talk about priority and quota. So what is a priority? Priority is exactly as the name sounds. It means the importance of the job. So they are positive integers that determine the importance of a task. So what this means is that a task with a high priority can overtake the resources of a task with a lower priority. So this is sort of an oversimplification because there are actually restrictions placed to prevent, like a string of higher priority tasks overtaking the resources of a lower priority task. So let's say you have a resource with priority 1, resource priority 1, and then, a job with priority 1, and then a job with priority 2 comes in and bumps out the resources of the job with priority 1, and then a job with priority 3 comes in and bumps out the job priority 2. And so nothing is really running. Things are just sort of being scheduled and starting to spin up until the other thing is being bumped out before the task can finish. The job can finish. And I'll just keep on going with so on and so forth. So you can look at the details of how this is prevented within the paper itself in section 2.5. The next thing that we can talk about is about quota, and this falls under the topic of admission control. And this is used to determine which jobs to admit to the cell for scheduling. Okay, so this is nothing to do with priority or anything. It's like if this cell doesn't have the resources for the amount of time that you specify, this job will not be admitted to the cell to be scheduled. So what you do is you specify the resources that you need, the priority that your job is at, and the length of time that this job needs to take up these resources. So what happens is if the cell cannot guarantee those resources to be available for that duration of time for the submitted job, the job is then rejected and is never scheduled. So for instance, the example that the paper gives, again, is, for instance, let's say you have 20 tibibytes of RAM at production priority from now until the end of December in cell XX. So that's like a two-letter identification of a cell to identify where the cell is in the world. And this is sort of, like the English phrase that we can think of is the question that we're asking the cell. Like, do you have these resources at this priority level for this amount of time? And if the cell says no, then the job is never submitted and is never scheduled to begin with. And so that is the answer to the question of what happens when more work shows up than it can be accommodated. And again, that's contextualized in the sense of what happens when jobs that need more resources at various priorities shows up than can be accommodated by the cell. Okay? Okay, so now let's go ahead and talk about naming and monitoring. So for this section of the paper, there's actually a lot more details than what I will be talking about. I won't be going through everything in this section. I'll just sort of be highlighting two things that I think are the most important to take away from this section. So far, we've only talked about creating and scheduling jobs and tasks. So the question that we need to pose is how do we find a task when it is rescheduled to a new machine? So for instance, let's say the task is unhealthy and Borg says we need to kill it or we need to restart it or somehow reschedule it to a new machine. How do we actually find it when this rescheduling happens? So what we have is, first of all, it's called a BNS name. So this is called a Borg name service name. And within this name, we have the cell ID, the job ID, and the task number of the task that it runs within the job. So the task number within the job. And this information, so this name, is then paired with the task's host name and port. So this is the, where we can actually reach this task. So this pair, so this name and then the host name and port, so this pair are then stored within a file that's managed by Chubby. Chubby is a lock service that I can talk about in later videos again. So this is all under the umbrella of distributed systems, which is really awesome to learn about and super fun because it solves really complicated problems in really simple ways. Well, maybe not super simple, but conceptually simple ways. Anyways, so with the BNS name, because it is paired with the host name and port within this file, Borg can now locate its tasks. So that problem is solved. In the paper, they'll later talk about how they sort of paste together this name and then attach it to a domain name to be located by the DNS service, but you can read about that on your own in the paper itself. And so for the monitoring section, we have HTTP servers actually built within the task itself. So remember, tasks are really just synonymous with containers, right? So what the HTTP server is responsible for is that it's responsible for publishing information about the container's health via a endpoint, via a health check endpoint. So for instance, if Borg says that the task doesn't respond within an appropriate window of time, or for instance, this task returns an error code, Borg can restart or kill this task so that the situation is handled. And that is the section for naming and monitoring. So that marks the end of the user perspective section, as well as sort of the overview of Borg. Next, what I'd recommend you to check out is my video on Borg architecture itself. So what's actually happening internally on a high-level overview. I would remind you to please use the paper itself as the main resources should you have any clarifications or you're interested in more details. All of this is derived from the paper itself, as well as other resources that I'll link down below. John Wilkes has actually a really awesome video where he personally talks about the paper himself, and he is one of the authors of this paper. So you can reach me at the Amy Code on Twitter should you have any questions, or if you want to tweet at me or you're interested in sharing my content, I would super appreciate that as well. Please follow, like, and comment, and I will see you in the next video. Thanks everyone, bye!